All right, our last lesson of the course is in chapters 10.3 to 11's booklet, and we're going back for 10.3. So go back to the beginning of the booklet, before you knew anything about permutations and combinations and stuff. Now, let's see, can I scroll faster? I think I can. I can shrink it, and then I can really go fast. Let's see, did that work? There we go. The very beginning of the booklet, go to 10.3. And let's talk about composite functions. First of all, did any of you guys have me in grade 10? I think some of you might have, right? And a function to me is a math thing that I think of. A function's like a toaster. I always use the toaster analogy. See, when you put in bread, out comes toast. So toasted bread. It's not like you can put in bread and get something out that isn't toast. You put in bread and out comes a Pop-Tart. You put in bread and out comes a bagel. I don't know what kind of magical machine you have, but it's definitely not a toaster. You see, the way I think of a function is a machine where when you put in x, you always get out the same output. Say f of x is x squared. Then you put in x and out comes x squared. You put in 2, out comes 4. You put in 3, out comes 9. Right? That's the way a function works. So, what if we started putting functions together in a way that you never did in grade 10? Like, what if I put a different function in as the input? That is what we call composite functions. So we would like to evaluate f of g of 2. And what this means is, if I put it in words, well, first g of 2. What does g of 2 mean? G of 2 means replace the x in g of x with the value 2, then evaluate. F of g of 2 means replace the x in f of x with the above result. So whatever I get from this evaluation is my x for f of x. So g of 2 would be, okay, we're going to put 2 in where that x is. 2 times 2 minus 3. Well, that's a 1. So f of g of 2 is like saying, what's f of 1? So f of 1 is going to be, put a 1 in where that x is, 1 squared plus 1, which is 2. Okay. Now, we don't have to put numbers in to functions. We could put a whole entire function. In this case, we're going to put a function into itself. So g of x is going to be me taking the g of x function and replacing the x with g of x. So instead of 2 times x minus 3, I replace the x with 2 times x minus 3. Right? So again, g of x here is 2x minus 3. So I replace this x with itself. And then I simplify it. It does say it wants an equation, but obviously it wants it simplified. So that's going to be 4x minus 6 minus 3, which is 4x minus 9. There you go. There's my equation for g of x. Putting a function into another and saying f of x or f of g of x has a shortcut way to write it down. It looks like this. This is the same thing mathematically as saying g of f of x. So again, we're kind of lower on the screen here. Let me copy the functions again. Don't forget, f of x was, what was it, x squared plus 1, and g of x is 2x minus 3. So put this function, or no, let me put that the other way. Take this function and replace this x with that function. Put this machine inside of that machine and see what it turns out to be. So g of f of x is 2, and instead of this x, I replace it with x squared plus 1. And then again, it says write an equation, but obviously we want our equation simplified. So I distribute the 2, and I get 2x squared minus 1. Okay. And then I want to evaluate what g of f of negative 1 is. Now, what I did earlier when I had to evaluate f of g of 2 is I actually found g of 2, and then I plugged that number into f of x. Well, now that I actually have a formula for f of g of any x, I can just say that that's no problem. I can use that as a formula now. It's 2 times negative 1 squared minus 1, which is 2 times 1 minus 1, which is 1. Please notice if I'd have gone the long way, and I'd have said, what's g of f of negative 1? And I'd have said, okay, what's f of negative 1? That would be 2. So what's g of 2? That would be 4 minus 3. Notice I get the same answer doing it that way. But if I already have a formula for what the two functions are put together, that saves me a lot of time. This is a really important idea in calculus. Finding a function of a function is something that's absolutely essential to a technique in calculus we call the chain rule. So those of you who maybe did that intro calc course, I think I've got a couple of you in here, you know what I'm talking about. This is pretty key as an idea. Okay, let's move on to a couple more here. We actually can do this non-equationally too. We can actually give you the functions in the form of a chart, right? So this is just a table of values. When x is 1, you plug 1 into the function and you come out with 3. You plug 2 into the function, you come out with 1. But for the other function, when you plug in 1, out comes 6. When you plug in 2, out comes 3. So what is f of g of 2? So first, let's find g of 2. When you plug 2 into the g function, out comes a 3. So I'm actually looking for what f of 3 is. What is f of 3? 3 goes into the function f of x, and it spits out a 4. Okay? What do we do with b? What's g of f of 0? Well, problem, f of 0 is not in the function. So, remember what D and E stands for? F of 0 does not exist. Therefore, g of f of 0 does not exist either. So there's no answer for that one, no solution. Okay, getting back to the ones that have solutions. Look at C. Let me make this a little smaller here. There we go. Look at C. Remember, this is a fancy way of writing g of f of 3. So work from the inside out. What is f of 3? Well, 3, when I put it into the f function, spits out a 4. So I'm looking for g of 4. 4, when I put it into the g function, gives me a 1. Okay. All right, we saw this on the other page. You can put a function inside of itself. What's f of 1 is what this is asking for. So run 1 through the f function, what do you get? Oh, you get 3. Run 3 through the f function, and you get a 4. There are lots of places in mathematics where you have to run numbers through a function, get the outcome, get the result, and put it back in as the input again. It's called iteration. If you've ever seen graphs of fractals, fractal graphs are a really good example of iteration. You put a number in and then you repeat the calculation with the output over and over again to infinity and then kind of look at what's happening. All right, this is kind of neat. Here's a function f of x, here's a function g of x. This should be familiar to you. This goes way back to chapter 2. What's g of f of x? So what I'm going to do here is I'm going to say, all right, g of f of x is, or actually I'm doing this one first, f of g of x first. So f of g of x means I take the g function and I replace the x in f of x with that function. So instead of 2 times x minus 3, it's 2 times g of x minus 3. Look what happens when we do that. The 2's cancel. 2 divided by 2 is 1. And I get x plus 3 minus 3, which is x. Interesting. Let's do g of f of x. So replace the x in this function with that function. So it's going to be 2x minus 3 plus 3 over 2. Does everybody get what we did? I replaced this x with that. And that bracket doesn't mean anything. So minus 3 plus 3. This is 2x over 2, which is again x. Hey, is it always true that f of g of x will equal g of f of x? No, it is not always true. And they won't always cancel down to x like this unless they are, remember this from chapter 2? Inverses of each other. It turns out that f of g of x and g of f of x both equal x. Therefore, I can say therefore f of x is the inverse of g of x. Or remember the notation for that? You could also say f, oh, I shouldn't say primed, I should say to the negative 1 equals g of x, right? Remember that's the notation for inverses from back in chapter 2? So there we go. So there's a neat thing. And now, we've done this with equations. We did it like this example here and back on the first page. We did it with a table of values. Now let's look at a graph. Let's use the graphs to find the question's answers here. Okay, so I can't really show you the graph and the question, so I'm gonna try to do something here. I'm gonna try to and new. I'm gonna capture that. There we go. And then I'm going to copy that and move that over. And let's see if I can just paste it right here. Nope. I need the cursor. I need the mouse to do that. Paste. Oh, it didn't do it. Oh, you know what? I think I want to paste it here. Paste as a picture. Yeah, see, if I do it the other way, it just thinks I want to add it to the page. Okay, and of course this is way too big. The technology. Okay, come on. Okay, come on, why aren't you? There we go. Sorry, it's being kind of laggy too. And then bring it over. Come on. There we go. That's what I was looking for right there. That's what I wanted. Sheesh. Okay, so what is f of g of 2? Well, on the g function, find me g of 2. So let's see. So g of 2. Well, when x is 2 on the g function, y is negative 1. So I'm actually looking for f of negative 1 because g of 2 is negative 1. So f of negative 1. So on the f function, when x is negative 1, looks to me that f of negative 1 is 4. Get it? I read the output from the input 2 on the g function, and that becomes my input on the f function. And the output turns out to be 4. All right. Next, what's g of f of 4? Okay, so f of 4, 4 on the f function, has an output of 2. So I'm actually looking for g of 2. And 2 on the g function gets me to negative 1. Interesting. Notice the relationship between A and B here? Can you kind of see the pattern to that? All right. Next, what is the value of x if f of g of x is 3? Ooh, thinking backwards. So I know the output to f of g of x. So think of, in other words, this is kind of asking the question in two steps. In 2 steps. The first step is, what's the input that gives us an output of 3 from the f function? So in other words, on the f function, when y is 3, which is right here, how much is f? Oh, well, it turns out f of 0 is 3, right? The x value is 0 when the y value is 3. So that means that g of x has to be 0. So what value on the g function gives me a 0? Well, hang on a sec. Looks like there's two answers, right? I get a y value of 0 in two places. So that's interesting. So this has two answers. So x could be 1 or x could be -2. This one has two answers. And you can do a check on this, right? You can check to see if these answers work by saying, all right, well, if those answers are right, then f of g of 1 should equal 3. And let's see if that's true. So g of 1 is 0, f of 0 is 3. Yep. And f of g of -2 should also equal 3. So g of -2 is 0, f of 0 is 3. Yep. So that is the right answer. So there we go. That's basically all there is to composite functions. Now we will do a couple of graphy ones, but for the most part, we're trying to get you ready for pre-calculus algebra or for calculus using pre-calculus algebra. So we're going to focus more on algebra. So the next page here, example 5, has a more algebraic one. Now, this one is different than all the others because notice that, or all the others we've done algebraically, because notice there's some things here that x can't be, right? So notice that the domain for f of x, the domain is that x has to be greater than or equal to -3, right? If you put in -4 for x, you can't square root it because you can't square it on negative, at least not in real numbers. So now this one's asking, determine g of f of x and identify the domain. Okay, well, let's do the algebra first. What's g of f of x? If I take this function and I replace this x with that function, what do I get? So if I replace this x with that, I get the square root of x plus 3 squared minus 4. Agreed? So that's what I get. So the square root of x plus 3 minus 4 is what I get. So, okay, now what happens when you square root something, then you square it right away? Well, those two operations cancel each other, right? Because they're opposite operations. So I'm going to get x plus 3 minus 4, which is x minus 1. Right? So there we go. So g of f of x is equal to x minus 1. Now it wants me to identify the domain too. Now I'm going to do that by kind of showing you what this looks like on Desmos. So let me see. I had Desmos open earlier, but I think I closed it. I did. Like a fool. All right. Desmos, open up. Are you going to be logged in as me? Yay, it's still me. So let's see. I had these worked out already. There it is. 10.3 examples. Okay, open the graph. So the first graph we graphed was, or the first equation we played with was f of x, which is this guy. And we already know domain-wise, this graph doesn't exist to the left of -3 because you can't square negatives. G of x is, of course, x squared minus 4. That should be very well understood by you. That's just a good old parabola. Notice that the domain of this thing is everything. You know why I never bothered to write that down, right? Let's put that down. For g of x, the domain is everything. Domain is, how do you say everything? You say x is an element of all real numbers, right? Because look at the graph, right? It's a parabola. X exists everywhere, right? It's getting bigger forever to the left and to the right. Those arms are opening apart forever. Now, the third equation we got, right? The answer we got here was, and I just realized I didn't put a bracket, was x minus 1. Now that's very well understood by you too. What does x minus 1 look like as a graph? Suppose I just said y equals x minus 1, and I graphed that. What would it look like? Well, it would look like a straight line. And straight lines go on forever, don't they? So you'd think the domain of this should be that. Should be all reals, shouldn't it? It goes on forever. Doesn't y equals x minus 1 go forever? Desmos sure thinks it does. But notice if I ask Desmos to do what we did algebraically and say, instead of just coming up with this equation, come up with it by going and plugging f of x into g of x. I'll get rid of the other two guys so you can see this clearly. And I'd click on that. Now, I don't know, can you tell that from your screen what happened? Notice the red line that represents g of f of x stops dead at the same place in terms of domain that the original function did. So even though x minus 1 as a function itself is going to have a domain that's everything, it goes on forever, because this thing wasn't really just x minus 1, it was the square root of x plus 3 all squared and then minus 4, which impacts its domain. So I'm going to go back to the notes here and I'm going to say that the domain for this thing, for g of f of x, my domain is the same as it was for f of x. X can't get smaller than -3. And I'm going to say this maybe as a note. I'm going to say this. Here's the rule kind of very formally. If at point C, f of c does not exist, then g of f of c also does not exist. Even if g of c is fine. Okay, so that's basically the rule. They have it as a note here at the bottom that says we must consider the domain of the inner function as well as the domain of the composite function. Think of the inner function. The outer function actually kind of doesn't matter. Let me show you what I mean. Let's find f of g of x. So f of g of x means, again, here's my two functions. Let me write them down again. What were they again? So f of x, you don't have to write this down. You can just look up, and I can't. F of x is x plus 3. G of x is x squared minus 4. So I'm putting this thing into that x. So f of g of x is the square root, and instead of x, I put in x squared minus 4. Okay, that bracket inside there doesn't mean anything. So this is x squared minus 1. Okay, now, can I simplify that anymore? No, that's as simple as I can make it. And if you remember your grade 11, do you remember what happens to a parabola when you square root it? Well, let's see. Let's go back to Desmos. See who remembers this. So, okay, so we're getting rid of this guy. So first I start with my parabola right there. And what happens when you square root it? Now think about this. We've talked about this earlier this year, right? I was going to say grade 11, but we did this year. Sorry, that's this course. When we square root this thing, remember we create or invariant points when y is 1, which I just, fine, I'm just going to put in 1. So let's see, what happens when I have g of x equals 1? So g of x is the parabola, right? Oh, whoops, wrong keyboard. G of x equals 1. There we go. There, right there, that point there. So what is this point? This point is 1 and negative 2.236. Okay, whatever. Yeah, you get the idea. Okay, so that point there and that point there are invariant points, right? Because the square root of 1 and negative 1 are the same thing. So, okay, I'm going to get rid of that. I just wanted to show you that that's the point we're aiming for. And those points don't change, but everything else gets square rooted. Notice you can't square root anything negative. So this part here doesn't exist. And when you square root everything after this, it's going to just curve that way and curve that way. And don't forget that between 0 and 1 for y, when you square root a number that's a decimal between 0 and 1, it actually gets a little bigger. So you expect a little bulge here. So that's what we're going to get. When we square root x squared minus 1, we get that, right? So we get the little bit of a kind of a weird, oh, wait a minute, that's the wrong one. Oh, it's supposed to be a 4, not a 1. Duh. Oh, there, right? You kind of have to zoom in to see the bulge, right? Let's see, zoom in. Can I zoom in? There you go. Yeah, there we go. We can see it there now, right? But that's exactly what we were expecting, right? We were expecting a invariant point at 1 and an invariant point at 1, and we were expecting exactly this graph, right? Let's see if that's what we get. Now, when we did this for the last one, we kind of got surprised. We were expecting x minus 1, but what we got was a line that kind of stopped dead, whereas x minus 1 goes on forever. Do we have that problem here? Is there any particular reason why this graph won't look exactly like what we're expecting? And the answer is no. This one's going to be exactly the same. Although, again, I just typed something wrong, didn't I? Wait a minute. X squared minus 4. Oh, hang on a sec. This is what I wanted. I don't know why I changed this. Hang on. This is supposed to be x squared minus 4. And when I square root x squared minus 4, I get the square root of x minus 1. No, I didn't. You know what? I did want 1. I'm sorry. Why did I do that? I don't know. I did want a 1. There we go. That's right. I wanted a 1 because I wanted the square root of... Yeah, that's right. I wanted that. And that's what it is. Desmos does... You actually have confused Desmos here a bit. You'll notice that it's like all these little dots here, which are kind of like dots saying, oh, these graphs run into each other. But then when you close in, it realizes, oh, yeah, you meant that it's the exact same line. This black line and this red line here are exactly the same thing. Let me get the parabola out of the way. Right, red line, black line, red line, black line. It's the same thing. So there we go. That is telling us the fact that these two are exactly the same, whereas these two were not exactly the same, right? One of them kind of just dead ends here. Tells us exactly what this note says. When you're trying to find the domain of a composite function, the inner function limits what the domain is, potentially, but the outer one doesn't. You only have to worry about the inner function and then the two functions put together. The outer function doesn't really matter. So for this one, the domain of this one is really only bounded by this, and this is, well, x is an element of reals. So the domain, I should say, maybe for f of g of x, domain is just anything you like. Well, hang on a sec. It's bounded by the outside function. It's not really all reals. Sorry. It is, of course, only going to exist between the places where you square root, right? So, well, let's see. Let's go back to Desmos again. So it doesn't exist. You can't square root negatives. So it doesn't exist at all between -1 and 1. How do you write that in a statement? Well, you'd say x can be anything less than or equal to -1. X can be anything greater than or equal to 1. And other than that, it's all real numbers. But notice this thing didn't have any problem. It's this guy, right? X had to be between those. So there we go. That's composite functions. So in the worksheets that you've been working on for chapter 10.311, come on, there we go. In your exercise book, we skipped the 10.3 section at the beginning. So now you can go back and try the 10.3 problems right here. You'll notice that number 1 and 2 are just like the first couple of examples. Then we've got a couple of graph ones, and then we've got some algebraic ones. So you can have the rest of this class to work on that. I'll stop the lesson now.